Hello students, welcome back. Now let's go to section 3, hypothesis testing for binomial proportions. This time we'll cover it with critical value theory. Critical value method, excuse me. Binomial proportions. Now what is binomial random variable? A binomial random variable is an independent repetition of Bernoulli random variable defined like this. Outcomes 1 or 0 and nothing else, and the probabilities p and 1 minus p and nothing else. Just 1 or 0, perfect for digital world. Now, if you apply the expected value and variance formulas, you're going to get these. The proof for expected value is easy, just a one-liner. Proof for the variance takes a bit of an effort. It takes algebraic manipulation. But in the end, we get these. Now here, apply the central limit theorem. Taking the average, we have the same expected value, the winning probability of Bernoulli, and the standard deviation, or the standard error, that's going to be sigma over square root of n. Eventually, you're going to get this. Square root of p1 minus p over n. Here's a sketch of proof. Same expected value. Alright, but here's the hard part, or here's more important part. Sigma over square root of n, and it can be manipulated like this. Now, why am I telling you this? Even though I'm not going to write a proof problem in this course. The reason is because of this. I've seen so many students making this mistake. That's wrong. N should be inside of the square root. Such a common mistake. Just a little symbol mistake and then get a wrong answer. And then from this wrong answer, you get everything else wrong from that point on and have a chain effect. A lot of things go wrong and you lose a lot of credit. All for what? Misunderstanding that n is outside of the square root. I want you to remember that because if you go back to the central limit theorem, then you have square root of n to begin with. N is inside of the square root to begin with. Alright, now let's go ahead and do some example problems using this essay formula. And here is a problem. The following is the blood type distribution table of the United States based upon a recent study published in 2008. And here is the source for that. Alright, here we go. And suppose that a random sample of 120 recent donations at a certain blood bank reveals that 78 were type A blood. Does this result suggest that the actual percentage of type A donations of this blood bank is higher than that of the national average listed above? Let's see what's the national average. We have Rh positive A and Rh negative A. Therefore, the probability for A-type blood is some of those. And that's going to be 0.420, 42%. Please check. And that's the national average. Now locally, however, we have the sample size of 150 and then a proportion of 78 over 150, and let's name it as X bar, and that's approximately equal to what? 78 over 150. Punch it into calculator, we get 52%. 0.52. This is a local figure. And let's compare. 42% versus 52%. Looks like there is a big difference. Or maybe not. It's just a coincidence. So let's set up hypotheses and test them. So, how will the null and alternative hypothesis work. Let's do this with the critical value method. Let's see. National average, 42%. Locally, 52%. So what do we have? That's gonna be the null hypothesis, and this is the alternative hypothesis, right? All good? Yep? Nope. Something's wrong. Please correct it. Go back to section 1 and check and then correct it if you cannot find out immediately. Here's the answer. These two numbers must be the same. 42%, 42%. Mu0 values must be the same. And these must not come from the sample. The null, NULL, that null means nothing. Must have nothing to do with the sample. Let's see, this 52% is comes from sample. So it should be 42%, and that should be repeated in both of those lines. One about the same as 42%, the other either greater or less. The problem says higher than, so yeah, higher than. Also, 52% is higher. So this description is wrong. Let's go back to national and local. And then here we have correct hypotheses. Now, some people may dislike the use of mu because this is not mean, it's a proportion. Well, in that case, you use pi. Pi for proportion. Letter P, and then the Greek version of that is pi. But whenever I use pi, and I see a lot of students getting confused because pi usually means something else, 3.14. So I'll try to avoid this. Even though our textbook author using pi, I'll try not to use it and then just use mu. And well, mean proportion or population mean, either way, I'm going to use mu. And there may be some people who dislike the use of mu. No, you have to use pi here. Well, it's my class, so I'll just use mu. Now, we have hypotheses set up, so let's go ahead with some numbers to work with, some sample statistics, and maybe some parameters. Let's see. Observed proportion is 52%, 78 out of 150. Okay, that's something we are going to compare at the very end. And standard error, square root of p, 1 minus p over n. And there, please note that I used a null. Not 52%, but 42% here. Why? Because that's a picture centered at the null. Picture explains everything, centered at the null, and that's what we use here for SE formula. Does it make sense? Graphically, it's clear. Everything is centered at this one. And by the way, if you remember what you did for the confidence intervals and confidence bounds for binomial proportions, in that case, you used observed proportion in the center. And you use observed proportion for this SE formula. You see, here, I'm not using this observed proportion of 52%. I'm using 42%. Why am I doing that? It's not because it's observed or it's a population mean or null or whatever. Actually, it has everything to do with the picture. You have to use the center proportion. That goes to this SE formula. You see, picture is really, really, really important. If you don't draw the picture, or if you draw inaccurately, you have to pay the price. The pictures are absolutely necessary. Draw the picture, that's easy, and then null is 42%, and then that's the critical value you have, and you have 1% alpha value, so that's the shading, 99% here. Basically, you're looking for something like the kind of computation as you did for 99% upper confidence bound to this and this critical value, and then you're going to compare that with 52%, you see. But in the process, you have to calculate the standard error. There you go. square root of P1 minus P over N, you use the center. The picture explains everything. And then once you get this critical value, you can compare that with 52%. If 52% falls here, close it off to null, then you take the null. If it falls here, then too far away from the null, then you ditch the null and then go with alternative. So blue is null region, red is alternative region. So once you find this critical value, that decision making is really straightforward. And that is the strength of this critical value method. Let me repeat it again. In the picture, which is absolutely necessary, once you get the critical value, it is very easy to make the decision because it all boils down to placing the x bar value, this observed mean of 52%. Does it belong to the null region of blue? Does it belong to the alternative region of red? Let's find out this x value, the critical value. How do you do that? Well, it's a z-curve, so you use z formula. End minus center over SE is x minus 42% over, well, SE computation is as you did above. I mean, this computation. If you do that, well, 0.04029, so 0.0403 approximately speaking. And that's what we have down here. And that's about the same as about 2.33. If you look up the Z table for 99%, you're going to get about 2.33. I use mathematical estimations to 2.326. I'll be more accurate, but if you look up the Z table, you're going to get 2.33. Anyway, you do your computation, you're going to get 51.4% approximately speaking. Very close, but 52% is still in the red region. You see, here's the full picture. Close, but still it's in the red region. All right. Now we're going to talk about the probability value approach in a separate video. If you're interested, go ahead. If you're not, then just skip that and go to section 4.